Hi, this is Kan-Lin speaking. I'm from the National United University Department of Energy Engineering. In the previous section, we talked about the air humidification definition. In this section, we're going to apply that definition to calculate the humidification of PEM fuel cell, proton exchange membrane fuel cell. This can be applicable for any other fuel cell and operate at low temperature. The air humidity, the gas humidity need to control. I use this example. I think this example is pretty good. We pick up from the textbook. I should put it down. I have to find out on the textbook, and this involved the energy and the mass balance. Is a quite good example. So this one is a humidification of the PEM fuel cell. This is the example. You can read this by stop the video and read it. But over here I use a schematic diagram to explain this example. For a fuel cell stack, the current density is 0.6 M per centimeter square, and the electrode area is 300 centimeters square. This stack is have the 60 cells connect in series, and then the humidification, humid air will be coming out. This fuel cell stack need to humidify the air at 80 Celsius degree, 100 relative humidity, and the pressure at 1.15 bar, and then the stoichiometric ratio is 2. The supplied air actually is cold, and the relative dry air is 20 Celsius degree, 60% relative humidity. The air pressure is 1 bar. So with that, we need to add the water to humidify the input cold and dry air. The water temperature is 60 Celsius degree coming in. So we had to humidify the air. Because the humidified air, the temperature is 80 degree, the water is 60 degree, the air is 20 degree. So we need additional the heat coming in, so to heat it up. So the question is how much air we need, how much water we need, and how much heat we need. So the question first is the air flow rate, and the second, how much amount of water should be added, and third is the heat requirement. The first, we calculate the air flow rate. The air flow rate from this example, we know the current from the Faraday law and the current density electrode area cell stack. We're able to calculate the molar flow rate of the oxygen required. So the molar flow rate of oxygen required is N cell times I divided by 4F. The number of cells is 60 cells connected in series, and then the current is equal to 0.6 M centimeter square, the current density, times the electrode area 300 centimeters square. So give you the total current output from the stack divided by 4 and F. This we got a 0.028 mole per second. This is oxygen required or the oxygen consumed in a fuel cell. Since the stoichiometric ratio is 2, so actually oxygen input is twice this amount. And then the air, if the air is oxygen molar ratio in the air is 21%, so we can, the actual air coming in is 0.260 mole per second. And if we know the average air molar weight, then we can calculate how many grams per second of air coming in. The result is 7.69 grams of air per second need to feed in to the fuel cell. So from here, we know the air required, the M air equal to 7.69 grams per second coming in. Since this air, the oxygen only contains oxygen and nitrogen, is a dry air base. So whatever coming in will be going out during the humidification process. Only the water content in the air will be changed, but the dry air will not change. The mass flow rate or molar flow rate of the dry air do not change at all. Next, we're going to calculate the amount of water required. So we already know the air flow rate on the dry air is 7.69 grams per second. I mark it as a red. Now, whatever coming in, then we need to calculate what amount of water need to add it in. So we had to calculate the amount of water in input at this dry air stream, and then the water content in the humidified air. Then the difference between these two will be the air required added into here. So first we look into the dry air, input dry air. The water content, the relative humidity is 60%, so phi equal to 0.6, and the pressure is 1 bar at 100 kilopascal. And then this is the water vapor at a different temperature. We call this a steam table, part of a steam table. And then from previous section, the water humidity and the mass ratio can be calculated by this equation. So the mH2 is a water molecular weight, m air is air molecular weight, and phi is a relative humidity, P is a PVS is a saturated water vapor at 20 Celsius degree. So we substitute all the number into the equation, and then PVS is a saturated water vapor, and then it's up at 20 degree. So from the steam table, at 20 degree, the water saturated pressure is 2.399. We substitute this number into the equation. We can calculate the relative, the humidity, the mass ratio is given by 0.00888 gram of vapor per gram of dry air. So the total water coming in the dry air is we had to multiply by the dry air flow rate, so it's equal to 0.068 gram of water per second. So we know the water coming in a dry air side. Now next we have to calculate the water going out from the humidified air. Similar process. The red is a calculated result. So now we had to calculate the water in the humidified air. So the water content at the humidified air, the relative humidity 100%, so phi equal to 1. And the pressure raised to 1.15 bar is 115 kilopascal. Similar equation over here, and then with the steam table here. The phi PVS, the saturated water vapor pressure, this is at a relative humidity 1, and then the 80 Celsius degree. So we look in the steam table at 80 Celsius degree, the saturated vapor pressure is 47.412. So substitute this number into the equation, we can calculate the humidity mass ratio base is 0.4377 gram of vapor per gram of air. So we multiply this humidity times the air flow rate, dry base. We can calculate the water in the humidified air is 3.366 gram per second. So the amount of water needed for humidification of air at the cell inlet is a difference between these two numbers. So we we subtract the water in the humidified air from the dry air. We add with a 3.3 gram of water per second needed from the water intake. So this number we know. And then the humidified air over here, we also know now. The next, we're going to calculate the heat required to reach, so the humidified air can be reached the temperature 80 Celsius degree. The heat required for humidification is over here. We put all the no number, put it in there for easy to calculation. And then the entropy balance, we had to do the energy balance. The energy input is the dry air inlet, and then the water inlet, and then the heat inlet Q, and equal to the air, the entropy outlet, humidified air. So we had to calculate each entropy, H air in and H water in, and then the H air out. Then we can calculate Q from this. So from the entropy from the previous section, we already know the entropy of air can be calculated by this equation. Over here, we don't count the water droplet because there's no water droplet inside the air. So XW was taken away. And then the specific heat for the dry air, vapor, and the water, and the latent heat or the heat of evaporation is given by this on the left corner. So we substitute those capacity heat, the number into the equation. We can calculate air inlet entropy. The first term is the dry air entropy. We times the specific heat of dry air and then the temperature 20 degrees, and then plus the amount of water in is a 0.00888 gram of vapor per gram of dry air, and then times the specific heat of the water vapor, and then the latent heat or the evaporation rate, evaporation heat of the water. So we end with that. Then the similar, we can calculate the air outlet. There's a different temperature and the amount of water content you can calculate. Then the water inlet is given by this equation, the specific heat times the temperature. So with this all in mind, we're able to calculate the entropy. Then we can calculate the heat required. We already know the air inlet entropy, air outlet, water inlet. So we substitute this, we can calculate the heat required is equal to 8.4 kilowatt or 8,380 joule per second. The heat required to able to raise the humidified air into 80 degrees. So this is a number, but also we can calculate fuel cell output electricity, because this fuel cell 0.6 amp per centimeter square with a 300 centimeter square the area. So output current is 180 amps, and then the cell voltage is each single cell is 0.7 volt per cell, and then we had 60 cells. So the output voltage is 42 volt. So output power is equal to voltage times the current is 7.6 kilowatt. So you can see fuel cell only output 7.6 kilowatt, and in order to humidify the air, you need 0.8 kilowatt. And since this heat is more than the power output from fuel cell, does it worth it? Probably not. But during the fuel cell operation, actually we don't need additional heat for this. The exhaust gas is a warmed air and then the effluent fuel. So actually the effluent, the exhaust gas can be do the heat change with the dried air. So actually, the heat required is recycled from the waste heat from the fuel cell output. So actually, there's no additional heat required